All right, so let's continue on. Today we're going to be talking more about dependent events. So, scenario, a bag contains 20 $1 bills and 5 $100 bills. Find the probability of getting 2 $100 bills. If you don't put the first bill back. Okay, so what I want to have happen over everything that could happen, probability. So find the probability of getting $200 bills if you don't put the first bill back. So there's all these bills in the bag, put my hand in, pull a bill out, don't put it back, pull another bill out. What's the probability that both of them will be $100 or $100 bills? Okay, so, well, there's 5. What I want to have happen, there's 5 $100 bills in the bag, and there's 25 altogether. $21 bills, $500 bills, so 25 altogether. Okay, so if I 5 out of 25, and then the second, but I set the bill aside. So assuming I got a $100 bill, there would only be 4 left on the second try, and there would only be 24 bills total. Okay, because I didn't put it back. So you have to adjust. It's not 5 out of 25 again. And then to find the probability, you still multiply. Now I would 100% reduce the fractions. And then 1 out of 30 makes for a 3.3% chance. Okay, so it's just you have to adjust for not putting the thing back that you were working with. Okay, so the total is going to be 1 less, and what you want, assuming that you want the same thing. So if I said, what's the probability of getting a $100 bill and then a $1 bill, then it's 5 out of 24 or 20 out of 24. You know, the $1 bills don't get smaller, the amount, because you didn't pull that one. So it's not always going to be 1 less on both of them. It will for sure be 1 less on the total. Okay, so don't just automatically take away 1, because it could ask you for something different. Like this, okay, where you take something out of the situation and then find like the probability. So the last handful of problems will be like, okay, let's look at another example. This one's more about comparing independent and dependent events. Independent and dependent. So the situation, I'm going to have to do a little bit of, just to make sure everybody understands. It says you randomly select 3 cards from a standard deck of 52 cards. And just in case you don't know what that is, I will go over that in a second. What is the probability that all three cards are hearts. When you replace the card each time versus not replacing the card. Okay, so in case you don't know, and that's fine if you don't, we have 13 hearts, 13 diamonds, 13 spades, and 13 clubs in a deck. In each of those groups, we have an ace, which could be counted as a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. So that makes the 13 like different cards. Okay, so it wants to know the probability of getting all three cards to be a heart. When you replace them, you know, I pull out a card, oh, it's a heart, cool. Put it back, shuffle everything up, you know, so it's not the same. Pull another one, oh, I got a heart, put it back, mix them all back up, pull a heart. Versus, I took a card, it's a heart, I set it aside, pick a card, it's a heart, I set it aside, pick a heart. Okay, so what we have is I want hearts. So we're going to do what's the probability that three cards are hearts when you replace. So I'm going to call the when you replace is the A version, and versus not replacing will be like the B part. Okay, so the A is the replacing each time. Well, there are 13 hearts out of 52 cards. I put it back, I mix it up, I want to get a heart. There's still 13 hearts out of 52 cards. Throw it back in, I do the same thing. There's still 13 hearts out of 52 cards. Okay, and so this is really, again, like I am never going to be multiplying 52 times 52 times 52, but if I reduce, it is 1/4 or 1 out of 64. 4 times 4 is 16, 16 times 4 is 64. Much easier to do that. So always reduce if you can. So when I do 1 divided by 64, I get 0.016. All right, so then when I don't replace the cards, well, I still have a 13 out of 52 chance. But I set the heart aside, and then you mix up the cards, and I want to get another heart. Well, how many hearts are in there now? There's 12. And now there's 51 cards. Okay, I set the card aside, pick another one. How many hearts are in there? There's 11 out of 50 cards. Okay, so because they were all hearts, it is, each of them gets less by 1. If it was, what was the probability of picking a heart and then a diamond and then a club? And you replace it versus you don't replace it. The A version is still the same because there's 13 cards of each kind. There's 52 total. When you don't replace it, the 52, 51, 50, that has to happen. And it could be 13, 13, and 13 if they want to do different things. Okay, so again, it could get replaced. So this one, to multiply it together, is a little bit more challenging because stuff doesn't reduce, nicely. So this is 1/4. But the other ones don't. Well, this one 12/51 actually does reduce. You can divide both of them by 3. So I get 4/17. It's not kind of a normal number. And then kind of dealing with fractions, I can reduce the 4s. So in the end, I get 11, and then 50 times 17 is 850. So definitely not as easy to get that multiplied together, but I get 0.013. So you are more likely, because this is, remember this is like a 1.6% chance, and this is a 1.3% chance. So you are more likely to get a heart each time by replacing the cards versus not replacing the cards. But how they want you to do it is like, well, how many more times likely are you to do that? So we kind of have to go back to using these like fractions, and you're just going to divide them. So it's 1 over 64 divided by 11 over 850. And so when we do that, we're going to go 1 over 64 times multiply by the reciprocal. And so we get all right, I had to pause the video because I had totally started coughing. I'm going to back up a little bit, and there's an easier way to do this. Let's, instead of doing the fractions, we're going to do 1.6 divided by 1.3, and it ends up being like 1.23. So we are 1.2 times more likely to get the A version than the B version. Okay, so just always, like, when whatever version of the problem is the more likely to happen, it could be the B versus the A. It doesn't have to always be the A that's better. Divide them, but the one that's more likely goes on top. So 1.6 goes on top, and the other one goes in the bottom. So you're always going to be, you're going to get a number that's bigger than 1 for your answer. So if you did 1.3 over 1.6, you're going to get, a number that's less than 1, which that shouldn't happen. Okay? All right. And then the last thing that we're going to do, this one where you're comparing independent and dependent. Last thing we're going to do is called conditional probability. So the scenario is we have like a quality control inspector checks for defective parts. And so it says the table shows the results of the inspection. So let's look at the table that they used. So I'm going to put D for defective and N for not defective. And then we have P for pass and F for fail. Okay, so it says the table shows the results of the inspector's work. Find The probability that a defective part passed. Find probability that a defective part passed and probability that a non-defective part failed. Okay, so the key is kind of in the wording. Okay, so the first part, find the probability that a defective part passed. So I'm only looking at defective parts. I'm not looking at all the parts. I'm only looking at defective parts and the number that passed. Okay, so I'm only looking at that line. Okay, so what do I want to have happen? A defective part that passed. So the number that passed is 3 out of 3 plus 36, or 3 out of 39, or 1 out of 13. Okay, which is 7.7%. Okay, which, I don't know, that could be kind of scary. If you have like a defective part of something and it still passed its inspection, 7% seems kind of high to me. All right, so then the second one, the probability that a non-defective part failed. So I'm only looking at that one. Okay, so the non-defective part that failed, there's 11, and then I need to add those two things together, 461, and then when I divide them, we get that, or 2.4%. Okay, so it's not like, and we'll talk about some of this stuff moving forward. It's not talking about like the number that were defective and passed compared to the whole thing. It's conditional. It's just defective versus not defective. We'll look at like what's the probability that a part was defective and passed. Not just the probability that a defective part passed. So we throw that and word in there, changes things, and that's going to happen in a later section. Okay, so just conditional probability, excuse me, is just one thing happened. Defective part passed. So 3 out of 39. Non-defective part failed. Okay? All right. So that should cover, you're doing 3 through 22. Yeah, the last couple, most of the problems are dependent. So that first, and then you're doing conditional probability. The last 1, 2, 3, 4. So it's 2 each. All right. So more probability stuff. Have a good day. We'll see you next time.